Okay, now we are going to dive a little bit deeper into the various different concepts involved in RTOS, starting with the idea of a task. So, what exactly is a task? We already saw that it's an independent unit of execution. Sometimes these are also called threads. And the way that we think about it is usually that there is a main thread similar to the main function in a C program, or it could be the main function in a C program, whose job is to create or spawn other tasks or threads, right? So the word spawn is sometimes used, which is basically to create. It's another way of looking at it, right? Now, once these tasks have been created, there is automatically a scheduler also has to come into play somewhere. We will look at the scheduler later, but the scheduler will be responsible for switching between the different tasks. So what we have over here is what I'm showing is basically an example of what the code for a task like this for a simple program involving two tasks would look like. Now, a couple of things. Many of these examples are things that can be run on the Walkway simulator. If that's intentional, right? It's so that you can also play around with it and see what happens. Which means that, interestingly enough, you might notice that we don't have a main function. Instead, we have the setup and loop that is used by the Arduino type code, right? Of course, in Walkway, you can also write regular C programs. But for all practical purposes, what actually happens is that the regular C program and an Arduino type sketch is actually translated into a C program and not through any complicated process. It is more or less just a preprocessor expansion that is done, right? Using the C preprocessor, we expand out this code into a full-blown C program and compile it. In certain ways, at least, this is easier to understand. But the interesting thing is that, as you can see over here, we are writing regular C functions, or rather C++ functions in this case. Why am I saying C++? The main thing is that we make use of certain functionality, such as, for example, the serial class, right? Now, if instead of this Arduino FreeRTOS, you actually included stdio.h and linked it with the regular functionality, you could use Preemptive and that would work as well, right? In the case of the Arduino, getting Preemptive working is a bit more complicated, so we are not really bothering with that right now. What we are going to do is directly, in the most cases, just use the Arduino code, but write our regular C programs and C++ programs and use them. Once again, I want to emphasize that the C++ that we use in this context is, just calling methods of classes. You don't need to know too much about what a class is or what object orientation is in order to use code in this manner. All that matters is you can think of it as a struct which basically has some data as well as some functions associated with it, and you can call those functions and you're done, right? You have the behavior that is required for using this kind of object oriented programming. We are not going to be creating classes of our own for the most part. Now, what is important over here, given that we are using the Arduino sketch approach, is that we don't have the main function. Instead, we are using setup and loop, and as you can see over here, loop is empty, right? And in fact, this is going to be a common feature in all the code snippets that we'll be looking at. We don't really have any functionality inside the loop function, right? Everything is done in setup, but if you look at what's actually happening over here, the first thing I've done is to set up the serial console so that I can print things on the screen. But after that, I basically create two tasks and I start this scheduler. Okay, so what does this mean, right? The exact syntax for X task create in this case, right, is not something that you need to readily memorize. It's not a standard C function. It is provided in the RTOS header. In other words, it's a library function provided by someone else, which means that in turn, the kind of parameters that are passed to this function, right, you will have to look up the API, the application programming interface documentation, in order to know exactly what these parameters stand for. I'm not going to go into detail on those right now, right? What is important is, you can notice, for example, that there is one X task create with the word task1, which actually refers to this function task1 out here, right? This string task 1 that we are using is something that is used for internal sort of housekeeping. Any error messages or debugging messages will use this word in order to show which task that error or the informational message came from. The rest of these things are related to certain things like the stack, the amount of memory available to the system, the priority and so on, right, which right now we are going to ignore. So if you leave aside all that, what you can imagine is happening is two tasks get created, right. What do the tasks do? A task, as you can see, is again a function, but it's an interesting type of function. It basically seems to be an infinite loop. Okay. So what exactly happens inside a task? I print a message and then I call this function vTaskDelay. Okay. And the purpose of a task delay is basically to sort of, in some sense, give control back to the scheduler, right. So what is actually happening inside this task is that by calling this vTaskDelay, and this 1000 divided by port tick is just a way of converting it into milliseconds, right. So it basically says delay by 1000 milliseconds. Okay. So what task 1 will do is it will print out the message task 1, and then effectively, for all practical purposes, it's telling the scheduler, okay, I am done, now wake me up after 1000 milliseconds. Okay. So this is something, you actually should pay attention to it. Normally, if I exit a function, right, I return from the function at the end of the function, right, I can return only at the end of the function. In other words, the for loop should have been completed and then I return from the end of the function. And the next time I call the function again, I would start once more from the beginning. If that was the case, why did I need this for loop at all out here, right? So that's not exactly what is happening. It's not that I'm returning from the function. What is actually happening is that the present state of the function is still there in memory. The stack corresponding to the function is still sitting there in memory. There are parts of the overall system that still retain the state or the context corresponding to this task. It's just that I have done sort of a branch or a jump from this back into the code corresponding to my scheduler, which in turn will jump back straight to this point, not to the beginning of the function. Okay. So when I return from the scheduler back into this task, I will be entering over here. If I had declared some variables out here, those variables would have the values that were last set, not something new that I am writing out here. Okay. What does task 2 do? It is also an infinite for loop, and what it does in turn is prints another message and then goes to sleep for 500 milliseconds, right. So effectively what you can imagine these tasks would do would be that, one of them keeps printing out the message task 1 once every 1 second, whereas this one prints out the message task 2 twice every second or once every 500 milliseconds, right. And this is important to keep in mind that they are not actually calling the function again and again from the beginning. The decision on when to wake up the task once more is determined by the vTaskDelay, which is set inside the task. It is not determined directly by the scheduler. The task tells the scheduler when to wake it up next. The scheduler will then later see, okay, which task needs to be woken up, wait for that much time and then wake it up next. Okay. Let's take a quick look at how this would look when we actually run it in a simulator like Walkway. So here we have the example that I showed you, right. It's, as you can imagine, right, a very simple piece of code. It just basically has the two tasks. It has setup, it has an empty loop function, and if you look at the hardware side, there is actually nothing connected because the only output is going to come on the serial port. So all that I needed to do was initialize the serial. So let's see what happens when I run this, right. As you can see, the messages straight away start coming out as, okay, I'm just going to stop this. Every time that there is a task 1 message, you can see that correspondingly there are two task 2 messages, then there is a task 1 message and two task 2 messages and so on, right. And the reason why is because the periodicity is different, right. What if I change this, let's say, to 800? So I have just let this compiled it with 800 and I let it run through for a little amount of time. It's not very clear, but if you sort of go through and count the number of 1s and 2s that are there, you will find that they are actually in an 8:5 ratio. Okay. Now we can do something better, right? We can actually go in there and I can declare a variable in each of these and print out the value of the variable, increment that variable, and I can do the same thing out here. And now we can start seeing that, as it starts printing out the tasks, each time this should sort of make it a bit more clear to you where exactly the thing is returning. In other words, I do not run this int count equal to 0 each time I go back and run the task. So it's clear that I'm not restarting the task from the beginning. I'm just basically taking over from the last point that it ran. And if we stop this at any point in time and we look at the numbers, for example, if I just let it run for a little more, you would have seen that this task 2 would have reached the number 50 at just about the same time that task 1 was reaching the number 30, right? Something to do with the ratios in which these different interrupts are, the different delays are being called. Okay, so can we exactly work out what should be the ratio and why these numbers should be coming out over there? Possibly. There could be certain sort of secondary effects which come about because of the fact that the serial print itself is taking a few milliseconds, right? And certain amount of the code that comes over here itself could add up to a few milliseconds. So even though we say 500 over here, it's not that it's exactly running every 500 milliseconds, right? It could be a little bit more than that. So the important takeaways over here, one is the fact that this count that I declare gets initialized once right at the beginning of the program, and thereafter it just keeps getting incremented and printed out over here, which basically shows us that every time I go through the for loop, I am delaying only by, or rather I'm returning back into that point in the for loop. I'm not going back to the beginning of the task. And it's also clear that the task delay that we are putting in, right, the scheduler is handling things in such a way that each of the tasks is being called at different rates depending on the amount of delay that you have requested from the task. Okay, so we just saw how tasks can run when actually put onto a microcontroller and compiled and run. So that also sort of tells us there are different states associated with a task. A task could be currently running, it could be ready but waiting for CPU time, it could be blocked, meaning that it's waiting for an event or a resource, it could be suspended, which is usually where it has been suspended by the application itself, or it could have terminated, meaning that it had a fixed amount of work to do, it completed the work and exited. This is actually exiting the function, right, as opposed to getting back onto the scheduler queue and then getting executed again, right. Now this exact terminology is not fixed, it depends on the OS you are working with, it depends on the system you are trying to build, but these are common terms that are used, right. In the context of what we have seen so far, normally we would say that while this printing is happening, for example, the task is in the running state, right, but once it calls vtask delay, it is basically blocking on the timer event, or it is in, it's basically ready to execute, but it's basically waiting for the timer event to execute so that it can then be called again and can start running, right. Now would that be in a blocked state or a waiting state? Blocked is usually used in the context of things which are waiting for a resource, right. So in this case it would basically be something else, but the exact terminology and how it is used, it's more important to understand what is the sort of idea behind it rather than the exact word that is used in each case. Now this diagram over here, looks a bit complicated, but this is essentially a state transition diagram, right? And understanding state transition diagrams is very important, not just in the context of embedded systems, in general for any kind of system design. It comes up all the time in digital system design, it comes up when in web applications, it comes up in graphical user interfaces, pretty much any kind of programming, right? And pretty much any sort of reasonably complicated system that you are trying to design can be thought of as evolving through a sequence of states. Now, in the present scenario, what we are talking about is these states correspond to the states of a particular task inside an application, right? So, I could, for example, have a task creation, after which the task goes into the ready state, right? Now, once the scheduler considers that the task is ready to run, it will transition it to the running state, right? Now, in the running state, multiple things could happen. I might find that I get an explicit suspend or rather a delete operation coming from the scheduler or from the operating system, which basically means that the task is killed, right? It no longer runs, it basically is just removed from execution altogether, its memory is freed up, whatever it was doing is cleaned up and taken out. Alternatively, I might find that I get suspended. And why would that happen? That could be, for example, something where the operating system runs out of memory or something else and decides that this particular task need not run, or the task might self-suspend. It might basically just go into a suspended state and wait for some other a resume event coming from the operating system in order to take it back to the ready state. Right? What is a usual series of transitions though is, while running, I might end up blocking, waiting for some kind of an event. It could be a timer event, or it could be a resource like a availability of a network card or a UART or a disk drive or something like that. If it turns out that some other task is using it at the same time that I ask for it, I go into a blocked state, right? And from there, as and when either the event occurs, let's say the timer expires, or the resource becomes available, I go into the ready state. I don't automatically go into the running state, because it's quite possible that multiple tasks might have been blocked and might free up at the same event, right? They all go into the ready state, and then the scheduler decides each one of them can be sent into the running state one by one. So, this diagram, even though it looks a little messy, is a good way of capturing the different sort of transitions within the life cycle of a task, right? It's particularly relevant in the context of RTOS or an embedded system, because you really need to understand the different states in which the tasks can be. But this of course is valid of pretty much any operating system as well. So, task management, right? These are functions that are provided to you by the OS, the libraries essentially, right? So, the FreeRTOS libraries will provide a certain set of tasks for you to run, and those tasks are basically things like, for example, the ability to create a new task. Those functions include creating a new task, which would basically mean allocating memory for the task stack, initializing the context, basically setting up any registers and so on, and finally adding the task to the scheduler's ready list. Okay. In the context of FreeRTOS, that function call is usually something called xTaskCreate. The first argument to that is a pointer to the task function itself, right, which basically says that, okay, this is where the function has been defined. This is actually a pointer to a function, and in C you can have pointers to functions, right. Task name is a string that's used more for debugging and so on. You can choose what you want to give it over there. You can also specify the stack size, and even though it says words over here, it actually means the number of computer words, the number of usually 4-byte values, right. There could be parameters passed to the task. In this case, I am just showing it as null, and something important over here is the priority, right, which is basically what should the priority of the task be. In other words, is it a high priority task or low priority task, right, and this in turn will determine if 2 or more tasks become ready to run at the same time, which one gets picked. Okay. So, it is important that you choose this carefully. If you decide for whatever reason that responding to a person playing the next button on a music player is more important than responding to the brakes being pressed, you could cause problems in the design of your car, right? So it's up to the designer to ensure that priorities are sort of assigned carefully. There are certain ways by which there can also be automatic updates of priority. Let's say that a particular task has not run for a long time. It could have its priority automatically increased to the point where it automatically starts to get a better chance of actually running on the system, because otherwise you have the possibility that very low priority tasks never get run. Now, just like we can create a task, we should be able to delete a task. In other words, once a task is completed, we remove it from the schedulers list so that it never comes back into the ready list. We free up any allocated memory, and if there were any resources that were being used by that task, we clean them up, meaning that we sort of free up any structures or data types that have been allocated for that, any memory that was used over there, and allow the resource to be reused if necessary or if possible. So there are different ways of looking at tasks as well. Some of them are the run once and exit, which is, for example, what happens in the setup, right? There might be tasks that you just run once when you switch on the system, right? They basically do a lot of initialization, setup and management, and then they exit. They are never run again until you restart the system. The forever loop is a very common sort of pattern that you come across in embedded systems. The examples that we looked at earlier, where you basically had infinite for loops, right? So the for semicolon semicolon basically is the equivalent of a while one loop. Both of them do the same thing. They basically say that whatever is inside the curly braces after that, or the next statement essentially, or the next block, is going to run forever. Now, what does forever mean? In the context of an operating system, it usually means that it does a certain amount of work and then it should call some kind of a task delay or basically go to sleep, right? Because otherwise it's not going to give up control for something else to work, right? And in certain kinds of operating systems, we have what's called cooperative multitasking. Cooperative multitasking basically means that each individual task needs to relinquish control. It needs to give back control to the scheduler, right? And by doing so, it says, okay, I ran up to a certain point, now I'm done, I will take a break, let somebody else run and then I'll come back later. That's cooperative multitasking, which if you can do it is actually very good, because it means that it can be done with a very limited amount of overhead. Each task just has to sort of pass control back to the main scheduler, which then takes care of eventually bringing control back to it. But things can go wrong. There might be bugs in programs, there might be other scenarios where a task does not relinquish control, in which case we have what's called preemptive multitasking. And preemption basically means that there is some other interrupt or a timer or some other scheduler task which wakes up at regular intervals and is extremely high priority, higher than everything else in the system, stops whatever is happening and basically says, okay, if something was running away out of control, I need to put a stop to it and make sure that others also get a chance to run. Okay. So the forever loop is fine, provided that you usually sort of have some kind of a task delay to give control back at regular intervals. But in certain scenarios, you might find that there are actually other sort of timer based threads that have extremely high priority and make sure that things don't just run away out of control. You could also have tasks that are completely event based, right, which even sort of starting the task is entirely based perhaps on an interrupt. And as we will see later, it's possible for an interrupt in turn to trigger a task and to basically trigger certain kinds of processing.